The cosmos presents a tapestry of staggering possibility. Across the star-dusted expanse, 100 billion galaxies wheel in a silent gravitational dance. Within our own Milky Way, a breathtaking census of stars numbering perhaps 400 billion offers countless cradles for new worlds. For decades, our search for life beyond Earth has been guided by a simple principle: follow the water. We look for planets orbiting within a star's habitable zone, that temperate belt where liquid water, the presumed solvent for life, could pool on a rocky surface. And in this grand cosmic hunt, one class of star has emerged as the overwhelming favorite. They are not the brilliant sun-like giants that dominate our stellar neighborhood. Instead, they are the unsung, unassuming majority of the universe. Dim, cool, and exceptionally numerous, these are the red dwarf stars. Accounting for nearly 90% of the total stellar population, they are the quiet bedrock of the galaxy. For astrobiologists, these tiny stellar embers once represented our greatest hope, a statistical certainty that life must be abundant throughout creation. Their sheer quantity suggested a near-endless supply of potential homes. Their lifespans, stretching into the trillions of years, offered an almost infinite canvas for evolution to work its patient magic. But a darker, more violent truth has begun to emerge from the twilight of these systems. A chilling realization is dawning upon the scientific community. The most common homes in the universe may not be sanctuaries at all. They might in fact be elaborate cosmic traps. New evidence suggests these diminutive suns are systematically stripping their planets alive, rendering the vast majority of the galaxy's habitable real estate a sterile, irradiated wasteland. The dream of a universe teeming with life on red dwarf worlds is dying. It is being extinguished by the very stars we believed would nurture it. To understand this cosmic betrayal, we must first appreciate the nature of these stellar bodies. A red dwarf is a celestial object of profound restraint. It sips its hydrogen fuel with incredible efficiency, burning at a fraction of the temperature of a star like our own Sunday. This cool nature dictates that its habitable zone, the region of life-sustaining warmth, is nestled incredibly close to the star itself. Imagine our sun as a roaring bonfire keeping the Earth warm from a comfortable distance. A red dwarf in comparison is a small glowing campfire. To feel its life-giving heat, a planet must huddle intimately nearby, often orbiting closer than Mercury does to our own solar furnace. This proximity is the seed of the first great peril tidal locking. Just as the moon is tidally locked to Earth, always presenting the same face, a planet in such a tight embrace with its parent star will suffer the same fate. The star's immense gravity tugs more strongly on the planet's near side than its far side, eventually halting its independent rotation. The world becomes locked in a permanent static gaze. One hemisphere is forever scorched in perpetual daylight. The other is condemned to an eternity of frozen abyssal night. Life as we comprehend it would be confined to a sliver of permanent twilight, a narrow terminator zone between these two brutal extremes. Here, in a ring of eternal dawn or dusk, temperatures might be just right. Powerful winds born from the stark temperature differential between the light and dark sides could theoretically circulate heat, perhaps widening this band of habitability. For a time, this was the great hope that complex atmospheric dynamics could moderate the planet's climate, transforming a world of extremes into a potential paradise. It was an elegant solution to a daunting problem, but this planetary predicament is only the opening act in a much more devastating drama. The true danger of the red dwarf lies not in its placid maturity, but in its violent, unpredictable youth. These stars may be small, but they are not meek. Particularly in their first billion years, they are fantastically active, possessing magnetic fields of astonishing power and complexity. This intense magnetism makes them prone to stellar flares of unimaginable ferocity. These are not the gentle flickers of a campfire. They are celestial temper tantrums, sudden and catastrophic releases of energy that can momentarily increase the star's brightness 1,000-fold. A planet orbiting in the close-in habitable zone is directly in the line of fire. It would be subjected to a relentless bombardment of high-energy X-rays and ultraviolet radiation. Such a blast of ionizing light would be lethal to any unprotected life on the surface, sterilizing the very ground upon which it might seek to evolve. But the flares deliver a more insidious, permanent form of destruction. They are often accompanied by coronal mass ejections, or CMEs, titanic eruptions of charged particles and plasma hurled into space at millions of kilometers per hour. This is the stellar wind transformed into a galactic hurricane. For a nearby planet, the consequences are apocalyptic. This particle tsunami slams into the planet's upper atmosphere with tremendous force. Over thousands and millions of years, this process acts like a celestial sandblaster. The planet's gaseous envelope is not merely damaged, it is physically scoured away. Molecule by molecule, the protective shield of air is ripped from the world and cast into the void. Without an atmosphere, there can be no stable liquid water on the surface. The planet's oceans and lakes would boil away under the low pressure, its water vapor lost to the unforgiving vacuum of space. The world is being stripped of its very essence, its potential for life systematically dismantled. Even if an atmosphere could somehow withstand this physical erosion, the intense radiation triggers a more subtle chemical assassination. High-energy photons, particularly extreme ultraviolet light, are exceptionally good at breaking apart molecules. Water vapor rising into the upper atmosphere would be dissociated into its constituent parts, hydrogen and oxygen. The hydrogen, being the lightest of all elements, would rapidly escape the planet's gravitational pull. The oxygen might react with surface rocks, or without a protective ozone layer, it too would be vulnerable to being stripped away by the stellar wind. The process is an irreversible desiccation. The planet literally has its oceans torn apart and bled into the cosmos. This presents a terrifying cosmic catch-22. A planet around a red dwarf must orbit closely to stay warm enough for liquid water. Yet that very proximity guarantees its exposure to the star's world-shattering flares and particle storms. The requirements for life and the conditions for annihilation are one and the same. The star offers a warm hearth with one hand, while delivering a sterilizing atmosphere-shredding blow with the other. The habitable zone is transformed into a kill zone. The promise of a cradle for life becomes the certainty of a planetary tomb, and the timescale of this destruction is crucial. Red dwarf stars remain in this hyperactive flaring phase for a very long time, often for the first 1 to 2 billion years of their existence. This period of intense violence coincides precisely with the time frame during which life is thought to have emerged on early Earth. While our own planet was enjoying the relative stability of a young G-type star, a hypothetical world orbiting a nascent red dwarf would be enduring a relentless billion-year-long assault. Any fledgling attempt at abiogenesis, the delicate chemical dance that leads to life, would be repeatedly reset by sterilizing radiation and atmospheric collapse. There is simply no window of opportunity, no period of calm for complexity to take hold. This grim scenario forces us to re-evaluate the very meaning of the term habitable world. A planet might check all the traditional boxes. It could be a rocky super-Earth possessing the right mass and composition. It could orbit squarely within the zone where liquid water is theoretically possible. But these factors are rendered meaningless if the stellar environment itself is fundamentally hostile. The character of the star is not a footnote, it is the dominant factor. And for the overwhelming majority of planets in our galaxy, that dominant factor is a small, furious star that actively works to destroy them. The statistical implication is staggering, and it directly challenges the optimistic view of a crowded universe. If up to 90% of the galaxy's stars are red dwarfs, and if the majority of their closely orbiting planets are subjected to this atmospheric stripping, then our cosmic neighborhood might be far lonelier than we ever imagined. The vast cosmic ocean, which we thought was filled with tranquil islands, may instead be dominated by treacherous, storm-tossed archipelagos. The search for life has been predicated on the idea that habitable real estate is common. This new understanding suggests that safe, stable harbors like our own solar system are the true rarity. But science is never a closed book. Could there be exceptions to this bleak forecast? Are there any circumstances under which a red dwarf world could survive and even thrive? One potential savior is a planetary magnetic field. A powerful, internally generated magnetosphere could act as a shield, deflecting the worst of the stellar wind and charged particles away from the atmosphere. Earth's own magnetic field is the unsung hero of our world's story, protecting our air and water from the sun's more moderate outbursts. Perhaps a large, rocky super-Earth with a rapidly rotating molten core could generate a magnetic shield strong enough to withstand the onslaught of a hyperactive red dwarf. The question then becomes one of strength. The magnetic pressure exerted by a red dwarf flare can be orders of magnitude greater than anything our sun produces. A planet would require a magnetosphere of truly epic proportions to offer meaningful protection. While not impossible, it dramatically narrows the field of potentially habitable candidates. The planet would need to be not just in the right place, but also possess the right internal geology, a much stricter set of requirements. Even then, a sufficiently powerful coronal mass ejection could still overwhelm the magnetic shield, triggering auroras that stretch across the entire planet and allowing deadly particles to rain down. The shield might prevent atmospheric stripping, but it may not prevent surface sterilization. Another avenue of hope lies hidden from the star's deadly glare beneath the waves. If a planet could form with an extremely large reservoir of water, life might not need the surface at all. Evolution could proceed in the dark, crushing depths of a global ocean clustered around hydrothermal vents spewing heat and chemical nutrients from the planet's core. Kilometers of water would provide an almost perfect shield against stellar radiation. The turmoil on the surface would be a distant, irrelevant storm. The planet's atmosphere could be stripped away entirely, leaving a barren, airless world with a liquid ocean sealed beneath a thick crust of ice. Such a world, like Jupiter's moon, Europa, or Saturn's Enceladus, could be a haven for life completely independent of the star's violent whims. This is an enticing possibility, a way for life to sidestep the red dwarf's fury, but it also presents a profound challenge to our methods of detection. We search for life by looking for biosignatures in planetary atmospheres, gases like oxygen or methane that are out of chemical equilibrium. An ocean world with no atmosphere, or one sealed beneath impenetrable ice, would be completely silent. It could be teeming with complex ecosystems in its hidden seas, yet it would present the face of a dead world to our distant telescopes. Life could be common but forever invisible to us, locked away in subterranean biospheres we have no way of probing. There is also the matter of time. Red dwarfs are violent in their youth but settle into an incredibly long and stable adulthood. After their initial turbulent phase, they can burn steadily for trillions of years. What if a planet forms later in the system's history? Or what if a world migrates inward from a distant frozen orbit? long after the star has calmed down. Such a planet would arrive in the habitable zone to find a peaceful, predictable star. It would have bypassed the early era of intense flaring entirely. This scenario allows for the possibility of ancient, tranquil red dwarf systems that are genuinely suitable for life. The challenge is that planetary formation and migration are complex and chaotic processes. Whether such a convenient late arrival is a common occurrence or a vanishingly rare exception remains an open question. These glimmers of hope, strong magnetic fields, subsurface oceans, late planetary arrivals prevent us from declaring all red dwarf systems to be sterile. They introduce nuance and complexity into what is otherwise a grim picture. They remind us that the universe rarely operates in absolutes. However, they do not change the fundamental conclusion. They transform the red dwarf problem from an absolute barrier into a series of immense filters. A planet doesn't just need to be in the habitable zone, it needs to be in the zone and have a massive magnetic field. Or it needs to be in the zone and be a water world with a subsurface biosphere. Or it needs to be in the zone and have arrived after the star's billion-year rampage. Each additional requirement dramatically slashes the odds. The vast pool of 90% of the galaxy's worlds is no longer a pool of promise, but a series of challenging obstacle courses, each with a low probability of success. The default state for a planet in a red dwarf's habitable zone is not a thriving Earth-like world, but a stripped, barren, and irradiated rock. Habitability, true and sustained habitability, must be the rare exception. This is a profound shift in our cosmic perspective. It suggests that the great silence of the universe, the eerie lack of detectable alien signals, might not be because life is hard to start. It might be because stable, nurturing environments are the true cosmic treasure. Our own solar system, once thought to be typical, is cast in a new light. The Sun, a relatively stable G-type star, is a paragon of stellar virtue compared to a young red dwarf. Its habitable zone is far out, protecting Earth from the worst of its solar winds. Its flares, while powerful, are infrequent and mild by comparison. Our planet was afforded a long, relatively peaceful childhood, a period of cosmic calm that allowed the slow, delicate process of evolution to unfold undisturbed. We may be the beneficiaries of a profound stroke of stellar luck. Our existence could be a testament not to the ubiquity of life, but to the precious rarity of a stable home. This realization does not mean we should abandon the search for life around red dwarf stars. On the contrary, it makes the quest more compelling, more focused. We now know what to look for, not just any planet in the zone, but a super-Earth with signs of a powerful magnetic field. We can search for the telltale signs of thick, resilient atmospheres that have somehow weathered the stellar storm. The recent discovery of planets like those in the TRAPPIST-1 system, a clutch of Earth-sized worlds orbiting a nearby ultra-cool dwarf, has transformed this from a theoretical exercise into a tangible scientific mission. The James Webb Space Telescope is now peering into the atmospheres of these very worlds, searching for water, methane, and the chemical fingerprints of a living world. What it finds will be a critical chapter in this story. If it detects dense, water-rich atmospheres, it will prove that some planets can survive. It will demonstrate that at least one of the escape routes, be it a magnetic shield or some other unknown protective mechanism, is viable. It would reignite the hope that against all odds, some of these worlds have made it. But if, as many now fear, it finds only the wispy, tenuous remnants of stripped atmospheres, or no atmospheres at all, it will serve as a stark confirmation of our darkest theories. It would be powerful evidence that the vast majority of the universe's habitable real estate is a cosmic mirage. The story of the red dwarf is a cosmic cautionary tale. It teaches us that a star is more than just a source of light and heat. It is an active, dynamic engine that shapes the destiny of its entire system. Its temperament, its history, its violent outbursts are the deciding factors in the story of life and death for its orbiting worlds. We have learned that the galaxy is filled with an almost uncountable number of planets in all the right places, yet they may be orbiting stars that are all wrong. The silent, ruby-red points of light that populate our night sky in their trillions are no longer just quiet neighbors. They are the sites of an ancient ongoing drama of creation and destruction. For every world that might by some miracle cling to its air and water, countless others have been scoured clean, their potential for life extinguished before it could ever begin. The search continues, driven by the knowledge that even if the odds are long, the discovery of just one living world around a red dwarf would change everything. But we proceed with a newfound humility, aware that a tranquil harbor in the cosmic storm is a rare and precious thing, and that our own blue marble orbiting its calm and steady star may be one of the rarest jewels in the universe.